Hello and welcome to Thermodynamics. The first lecture in the series is on kinetic theory, and the essential question is, how can kinetic theory help us to explain and predict the behavior of thermodynamic systems? So the first thing to kind of define is, what is kinetic theory? Because kinetic theory is sort of the model we're going to be using to explain everything in thermodynamics. Kinetic theory basically says that a system of gas consists of a whole bunch of tiny little particles, and most importantly, and that's probably what you knew before, but most importantly, those tiny little particles are moving all the time. They never stop moving. They never stopped moving since the Big Bang. And because they're moving around and they've got mass, they're also constantly colliding with the container walls and with each other. And understanding the way those tiny particles look is going to give us the key to being able to make predictions and calculations. This is a sort of a simulation of what these tiny particles look like. And you can see that if you try to follow one of those dots, it actually moves around pretty fast in the system. But also its direction and velocity is changing all the time due to these collisions. So in thermodynamics, we're going to be learning how to basically deal with pressure, temperature, and the volume of gases, which can all be predicted and explained by adding what's called the kinetic contributions of each particle of gas. So each particle of gas acts like a Newtonian object that's moving around and has kinetic energy. But the gas sample as a whole is basically a result of all of these tiny little particles, not just the motion of the whole object. It's going to be the things inside the object. So the heart of all science is experimentation. So the question is, what things can we measure or know about gas particles in the system? The first thing that we're usually going to be given in a physics problem is some information about how many gas molecules they are. Figuring that out is actually a little bit more chemistry than physics, so we're going to mostly be told how many molecules of gas are in the system. The one little catch is that there's a lot, right? There's a lot of gas in a sample of gas, and so we don't measure it in molecules typically. We usually are given the number of moles of a molecule, and moles are essentially like a dozen. It's a system of categorizing particles into a bundle that's a lot easier to keep track of than individual particles. So 1 mole of a gas is the same as 6.02 times 10 to the 23rd molecules. That's known as Avogadro's number. It lets us just convert back and forth between moles and particles, and that's given to you on your AP equation sheet as well. So if you were told you had 3 moles of a gas and you wanted to know how many particles that was, just 3 times that number, which is a lot, and that will tell you how many particles you have. The second thing that we're going to usually be able to know about our system is the mass of one of those molecules as well. So we can figure out the mass of a molecule using periodic table. So people have taken measurements over the years to figure out how much do each atom weigh, what's the mass of each atom. And so you can use a periodic table to figure out what is the mass of, like for example, water, which has got 2 hydrogens and 1 oxygen. What you would do essentially is sum up the atomic numbers or the atomic weights, they're close enough for physics sakes, to figure out the mass of 1 H2O, right? So H2O has 2 hydrogens and 1 oxygen in it, so the mass of a molecule of H2O is going to be 1 plus another 1 plus 16, which is essentially 18. 18 what is a good question. 18 atomic mass units, which we'll talk about later on, is the mass of a single molecule. But typically in chemistry, you think of this as the number of grams a mole of these particles had. So if you had 1 mole of water or water vapor or any kind of any state of matter for water, the mass of that mole would be 18 grams. The next thing that's measurable is the volume of the sample, and that one's probably the easiest one for us to handle because a system of gas is going to, by definition, fill the container, right? This is where gas is a little bit different than liquids. Liquids kind of sink to the bottom, but gas is spread out all over. So that means that if you can figure out the geometry or size of your container, you're also going to know the volume of the sample. And the last thing that is measurable or knowable is the temperature. And we would use a thermometer or a thermocouple or a probe of some kind to measure the temperature of a system. And you're pretty familiar with how thermometers work, I'm sure, from previous science classes, but we're going to learn more in this unit about what is actually happening in a thermometer and why does the temperature of a gas change when we make different changes to the system. A couple things you should know going in is that the temperature of a gas system is related to the speed of those molecules somehow. And gas molecules, as we saw in the last slide, are moving around a lot. They are vibrating back and forth. They are rotating, which is spinning. And they are also translating, which is what we typically think of as velocity, or moving around the sample. Those things are moving really fast. The translation velocity is on the order of 1,000 meters a second, how fast gas molecules are moving around the system. And that's what we're going to be using eventually to kind of figure out what do we mean by temperature. So the next question is, based on those measurements that we took, or that we can take from our sample, what are some more calculatable variables? The first is the pressure on the sample. And so we got a handle of a little bit of what pressure meant in fluid dynamics, and this is going to add to our understanding of pressure based on kinetic theory. The other thing is that we'll be able to, using the temperature, actually figure out that translational velocity, or the speed of the molecules. I like this comic because it sort of shows that hotter things, higher temperature things, have more energy. They're moving faster, and that is consequently why they can damage our cells sometimes when they hit us, because they're actually hitting us with a lot more energy than something that's moving. So anyway, we'll be able to calculate that when we understand a little bit more about temperature. So in the last unit, we talked a lot about pressure, and hopefully you'll recall that we defined pressure as the force acting on a surface divided by the area of that surface. In this unit, that force comes from the collisions of the gas molecules with the walls of the container. Every time a gas molecule hits the wall, it pushes on that wall, just like if it was a tennis ball and it was hitting a tennis racket, it would exert a force on the tennis racket as well. One note about these collisions is that we define them as elastic, which means those are special collisions that don't lose any energy, right? When your tennis ball hits the racket, it doesn't bounce off at exactly the same speed it went in on. It's going to go a little bit slower on the bounce off because it loses some energy and friction. But for molecules, kinetic theory assumes that they are perfectly elastic, which means if it comes in at 2, it's going to bounce off at -2, and it's going to exert a force on the wall in the process. Now, the collisions with the other molecules might cause the velocity of one of those things to change, but if one of them loses kinetic energy, the other one is going to gain the kinetic energy. So inside the system, the collisions are transferring kinetic energy to each other. We're not transferring the energy to the wall, just to the other particles in the system. So if you think about, if you were trying to come up with an experiment or an equation, or think about what variables might be used to calculate what is the force on the wall due to all these tiny little collisions, like imagine yourself in a room of tennis balls and you were trying to figure out how much force would be exerted on the walls. Like, what things about those tennis balls would you care about? Well, the mass of the particles, right? The heavier the balls are, the more force they're going to exert on the walls, which is why we needed to be able to calculate the mass of the particles from the periodic table a couple slides ago. So there's a linear relationship between the force and the mass. The heavier the particles, the more force they're going to exert on the wall. The second thing is how many molecules there are. So if you had a lot more of those molecules, obviously overall we're going to have a lot more. So the number of particles is going to determine the number of collisions every second, essentially, and that's going to be translated eventually into the pressure as well. And that's also linear, which means doubling mass or doubling N will double the force, which will double the pressure, because force and pressure are also linear. The third thing that has a relationship with force is going to have to deal with the velocity of those particles. Specifically, how much does their velocity change when it hits the wall? Because the wall is basically stopping that particle and then pushing it back the other direction. So it's the delta V that is going to be relevant here in the force. A little quick note about that, right? Remember we said if that ball, if it's an elastic collision and the particle comes in at 2 and it bounces off at -2, so delta V in that case would actually be 4 because we're changing by 4. So that's a little nuance, but it comes up in problems. So the faster the particles are moving, the more force they're going to be exerting, and thus the more pressure they're going to be exerting on the containers as well. So a lot of the problems in this unit are not actually ones that you have to solve numerically. Instead, you're going to be using something called proportional thinking to sort of explain how changes to some variables in the system will affect the others. So when you're given this kind of problem, you want to kind of imagine or create this train of proportionality. Say, when I change this variable, it's going to affect this one, and how? And then how will that then affect this one, and so on down the train. The effects are sort of cumulative. They build up and add to the eventual effect via multiplication or division. So you're going to multiply together the effects of all of the changes until you get your final effect. So here's an example of a problem. A solid cube of side length L contains a certain molecules of gas, N, moving with masses M, average mass M, moving at an average translational velocity V. In this state, the pressure on the walls is P naught. You're probably saying at this point, where's my numbers? And you're going to get comfortable dealing with variables as we move forward. So you will face a question like the following. If half the gas is removed, but the velocity of the remaining gas triples, how will the pressure in the cube change? So I'm going to consider these effects separately and consider how their effect will basically combine to result in what's happening to the pressure on the cube. So first, if you take out half the gas of the sample, you can sort of picture that means that the N is going down by a factor of 1/2, and that means that we're going to have less collisions with the wall, right? By, again, a 1/2 is going to be the proportion. So if we have half as many collisions with the wall, that's going to make the force go down, also by a 1/2, and force is going to make the pressure go down by a 1/2 because of all of these proportionalities. The second relationship is the velocity of the gas tripling. So if we triple the velocity of the gas, now, if I just consider that effect by itself, those little particles are hitting the walls much faster, 3 times faster. And that's going to mean that each collision is going to have 3 times as much force, which is going to cause the pressure to go up in theory by a factor of 3. So what I essentially would write down on my paper is that N and V both are proportional to F. That means whatever changes happen to N or V will do the same to the force. And force is proportional to pressure. So whatever happens to force is going to happen to pressure. So it's just it's just going to come down to multiplying together those two effects to figure out what's happening with pressure. So having N is going to have F, which is going to have P, but tripling V is going to triple F, which is going to triple P. So my net result is that we tripled and we have, and then we're left with basically 3/2 of the original pressure as our final pressure. So you can see we kind of made this train of reasoning to come up with our net result using proportional. So let's talk about how temperature fits into this kinetic theory system of model of viewing thermodynamics. The variable that you have known in the past as temperature is defined as being proportional to the average kinetic energy of a system of particles. We're going to break this down and go into the proportionalities a little bit later on, but here's the fundamental idea. If you've got a cool gas, right, that means the particles aren't moving very fast, and that means that A, we have less collisions because it takes them longer to get across the sample and run into the walls, and B, each collision is less energetic because the molecules are not moving very fast. If you have a hotter gas, we have more and more energetic collisions, and so this is why it makes sense to think about temperature as having to do with the energy of each of those molecules of gas. Temperature in this class is measured on the Kelvin scale, which is equal to Celsius, which you may be a little bit more familiar with than Fahrenheit, plus 273 degrees. Hopefully you've been experiencing that in chemistry a little bit, so that won't be too much of a shock. But when you see a temperature of 273 Kelvin, that's freezing point of water. 0 Kelvin, of course, would be theoretically the temperature at which, things have no motion at all and are therefore not colliding with the container walls. That's known as absolute zero. Most of the time, we're going to be dealing with, multiple hundreds of degrees Kelvin because we're talking about gases and they have to be above 373 Kelvin is going to be the temperature of boiling point for water. So typically speaking, we're talking about 300, 400, 500 degrees Kelvin. So if you knew temperature, which is pretty easy to measure using a thermometer, we can actually calculate the kinetic energy of a gas sample from this temperature. There is a conversion known as Boltzmann's conversion, and this is in your equation sheet. And it basically says that the average kinetic energy of a sample of gas is equal to 3/2 times this weird random number, 1.38 times 10 to the negative 23rd times the temperature. And I'm calling this a conversion because there's not really variables in here. We're just going back and forth between temperature and Kelvin and kinetic energy because they're proportional to each other, but there's no other variables that affect temperature. The only thing that temperature depends on is kinetic energy. So there's not really variables in this equation. It's really more like a conversion. But I'm going to remind you that when it comes down to figuring out that kinetic energy, the kinetic energy of an object is equal to 1/2 times its mass times its velocity squared. So if we wanted to know how making changes with the individual particles of the gas affect its temperature, it's a little bit more complicated. The temperature then is going to depend linearly on the mass of the gas. So if I have two samples of gas that are identical in motion and in everything except for one of them has twice as much mass, the temperature of the sample with more mass is going to have twice as much, is going to be twice as high because each of those particles has twice as much energy. So when it hits the container wall, it's going to exert twice as much force and it's going to be twice as energetic. The other variable that's going to impact the temperature is the velocity, and that's what we kind of talked about earlier. But the velocity, because of that v squared component of that equation, means that the velocity matters more. Velocity matters more than the mass. So when you double the velocity of a gas particle, you actually quadruple its kinetic energy, which means that we're going to be quadrupling the temperature. So that is called a quadratic relationship, and it's sort of important that you realize that both increasing mass and velocity have a net effect of increasing the temperature, but increasing the mass makes it linear. Increasing the velocity is a quadratic increase. It's going to cause that temperature to go up really fast if we double our velocity or more. You may be able to predict that there's going to be a lot more proportional thinking kind of questions related with temperature based on those relationships. You may see problems that mention a thermodynamic system. A thermodynamic system is going to be a sample that contains a lot of gas particles in a state known as equilibrium. Now, equilibrium does not mean that every gas particle has the same velocity or that they're all staying still or anything of that nature. It just means that those particles are only transferring energy to each other. So those particles are running around, they're colliding with each other, they're going to be transferring that kinetic energy back and forth, but it's at equilibrium because within the system, the only particles that are gaining or losing kinetic energy are each other, and when one loses some, the other is going to be gaining the same amount. If you actually could record the velocities of all the particles in the system, you would find that those velocities would be a bell curve distribution. That means if you took the percent of particles that had every velocity in a system, you'd find that there's going to be some very, very slow particles in every thermodynamic system, and there's going to be some very, very, very fast hot particles in that thermodynamic system. But most of the particles are going to be found sort of in the middle, the average speed of the particles. And so if you look at a graph of the percent of molecules on one axis and their speed in the middle, there should be a peak or a place where most of the molecules sort of fit. And that is what we're going to be using to simplify our life in thermodynamics. We're going to assume that all the particles act as if they are an average particle, even though we know that's not actually true. But the peak, the value of the velocity at the peak of that curve is what we will be using to calculate the average kinetic energy and therefore find the temperature of any sort of sample of the whole system. Okay, even though individual particles are different, the average is going to hold for the system as a whole. And I sort of mentioned this above, but it's important to note that the overall kinetic energy of a system and therefore the temperature of the system is going to be conserved. That means we're not losing any energy in these collisions. Even though it's going to be different particles at different points on this bell curve, the total temperature of the system should be conserved. Okay, we've reached the end of this first video. Hopefully you now have a better sense of how we're using kinetic theory, what kinetic theory is, and how we can use it to help us explain and predict the behavior of different variables like pressure and temperature in a thermodynamic system.